Hello everyone, my name is Krish and today I will be presenting this PPT on LVDT and its characteristics for the CWS presentation of my course PHN 310 Applied Instrumentation. The content that I would be covering in this topic are: what is LVDT, how is it constructed, what is it made of, what's the construction of LVDT, operating principle, the principle it used, the working principle of LVDT and that stuff. Then the characteristic, the output of what LVDT gives, and the advantages and disadvantages of this particular device, the applications of LVDT, and the linearity of system, and how to increase the working range, that is the working linear range of this particular device. Let us get into it. What is LVDT? One second. What is LVDT? Here we look at a image that explains what is LVDT. LVDT is basically something that has two coils, one a primary and secondary. And a secondary, there are two parts of secondary coils. There is a moving core. There is an input voltage that is applied to the primary, and we check the output voltage. I will explain all this in the working and operating of LVDT. Let us understand what is LVDT. LVDT is an acronym for Linear Variable Differential Transformer. It is an electromechanical transducer that can convert the rectilinear motion of an object into an electrical signal out. Here the object is the moving core and it is being checked by the output voltage here. And what is the output voltage? It is an electrical signal. The LVDT is a secondary transducer. What do you mean by secondary transducer? The input such as force, weight, tension, pressure are first converted into a displacement, and this is done by a primary transducer, and the displacement is then measured by LVDT. So therefore LVDT is a secondary transducer. Now it is called a differential transducer because it measures the difference between the voltages of the two secondary coils. Let me read this. Its electrical output is obtained because of the difference of secondary voltages, as I said, hence it is called an differential transducer. This transducer is an inductive based transducer and is very accurate compared to the other inductive based transducers. Let's get into the construction of LVDT. Construction. Here we see the image of how LVDT is made. The LVDT consists of a primary coil, a core, a foam, two secondary coils outside the primary windings, and some other stuff. The transformer's internal structure consists of a primary winding. Here we can see this golden thing is the primary winding here, the center one, and a pair of secondary windings which are both identical on the right and the left side of primary windings. All this is placed inside a hollow foam, and it is made sure that the foam does not allow outside inductive interference. Now a movable soft iron core is placed inside this hollow foam, and it is ensured that there is a little difference between the outer radius of core and the inner radius of the hollow form to ensure smooth movement of the core. Now the primary winding is supplied an AC voltage that is called an excitation voltage, and it produces flux. This flux is then measured across the secondary voltages due to the movement of the core. Hydrogen annealing is done on this iron core to reduce harmonics, residual voltage, and other stuff to get high sensitivity. Both the secondary windings are connected in such a way that the resulted output is the difference between the voltages of two windings because of the motion of the core. Let's get into the operating principle that we were talking about, how the motion of the core gets us a differential output. The working principle of LVDT is based on the mutual induction principle. As we said, we provide excitation voltage to the primary winding, which induces flux, and that is transferred through the moving core to the secondary voltages, and thus there is a mutual induction between the primary and the secondary voltages. Now, the what we measure is the difference between the induced EMF in secondary winding S1 and the induced EMF in the secondary winding S2. E output is E1 minus E2. Now we have three different cases of what can happen between E1 minus E2. When the core is to the maximum left of its position, such as it moves towards the S1 side, the flux in S1 would be more than the flux in S2. And therefore, the EMF in S1 would be greater than the EMF in S2. And thus, we have an output voltage E out, which is positive and in phase with the primary voltage. There is a second case where we have the position of the core at the null position at the center. And here, the flux in S1 and the flux in S2 are equal. And thus, we get no output, zero voltage. And after that, when the core moves to the rightmost side of the its rightmost side towards the S2 side, the flux in S2 is greater than the flux in S1. Thus, the EMF in S2 would be greater than the EMF in S1. Therefore, we have a voltage that is in opposite to the phase of the primary voltage that is applied to this primary coil. Now, what are the characteristics? As we said, we have a voltage here that goes to 0, and when it goes to the S2 side, the voltage again increases to the same position. This is the characteristic curve, which is the difference of the movement of LVDT and the output measurement. To check what it is, when we plot this, we get a linear range from here to here, and after some range, the linearity decreases and it becomes non-linear. Output versus core displacement is the characteristics. The amount of change in voltage, either negative or positive, is proportional to the amount of movement of the core, and it is a linear movement. The output voltage is a linear function for a certain range, of course. The A shows how the magnitude of the differential voltage E out varies with the core position, and the E out at maximum core displacement from null depends on the amplitude of the primary excitation. And at the center of the displacement, it is null, as we said earlier. The EMF generated in both S1 and S2 are 0. Will be equal, therefore E out would be 0. And the figure 3C shows the linear range of the LVDT. LVDT characteristics, advantages and disadvantages. Advantages. Let us first get into advantages. The LVDT has a smooth and wide range of operation. The LVDT works on a wide range and it is smooth and it gives accurate results. It is high sensitivity. A very minute difference in the displacement would be showed up on the results, the characteristic curve. There is low hysteresis loss. When we repeat the experiment multiple times, we would get the same result and nothing else. There is low friction losses. As I said, there is a difference between the hollow core inner radius and the outer radius of the core. Therefore, we have less friction between the, as this is EMF based, we do not have contact between all the equipment. The rugged operations, as the hollow core or hollow foam is very lightly made, it can be used in rugged operations. Low power consumption, only a primary excitation is required in the primary voltage. Other than that, nothing is required. And we have a direct conversion to electrical signal, which can be passed on to data analysis and anything digitally. And it has a fast dynamic response, as I said. Fast movement of the core can be measured by the LVDT. Disadvantages, it is sensitive to stream magnetic. As the principle depends on electromagnetic induction, stream magnetic field can affect the result of LVDT output, and it also affected by vibration and temperature. Vibration may lead to displacement of core, and thus it can give out bad results. Linearity range is very small for a particular size. So for a particular size of LVDT, we have a particular range from some centimeters to some centimeters, and which is a disadvantage in some cases. Therefore, people try to increase the linear range of LVDT applications. Here we can measure the weight of a system. The movement of LVDT here will give us the displacement, as this is the secondary transducer and this is primary. Both is converted into a displacement of the LVDT core, and thus we can measure it. LVDT is used to measure displacement ranging from a fraction of millimeters to few centimeters. LVDT can also act as secondary transducer, as earlier mentioned, and it converts electrical signal. It is mostly used in industries as well as servo mechanism, and it is also used in industrial automation, aircraft, turbine, satellite, hydraulics, and many places. Linearity of the system, as we were talking about. Here we had this particular characteristic graph of the LVDT, and here this particular range, this small range, is only where we can get a linear response of the LVDT displacement, and which is very useful in doing analysis of multiple stuff. There are several synchronous demodulators to obtain the core portion signal. So this signal E out is converted into a is sent to a demodulator to get the core portion of the signal. And traditionally, this is done by analog multiplier and low pass filters to extract the core position signal. However, the range of this is very narrow due to the structure of the LVDT. And if you want to increase the range, you have to increase the size of the LVDT, which is not possible in some of the applications that we mentioned earlier. The measuring range of LVDT offers a narrow linear range due to its non-linear transfer characteristics. What do you mean by non-linear transfer characteristics? These demodulators that are being used work on a transfer function, and this transfer function has a very shorter range. It can be seen that linear measuring range is linear only in the range of zero crossing of its transfer characteristic curve. This is obvious. The linear measuring of range of LVDT can provide a wide measuring range to meet such requirement by increasing the structure size of LVDT. But as mentioned earlier, it is not very feasible in many of the cases. So my project that I am currently working on works on how to increase the range of LVDT of a particular size just by changing the demodulator circuitry. As you saw earlier, LVDT has a very small linear range to work, and if we want to miniature LVDT and we don't want to use bulk LVDT, we have to do something about it. And in the paper cited below, it uses a external circuit after demodulator to increase the range by approximating the transfer characteristic as a hyperbolic sine function using electron. Here is the paper that is mentioned. The proposed circuit here is the circuit that the paper mentions. Increases the range from plus minus 2.454 millimeter to 6.2 millimeters. That is a 300% increase in the range. And while reading about this project, I also thought, how could someone increase the circuitry by using, not by using external circuitry, by using something else. And that is when I came across another paper that I have cited here. If you want, you can check it out. I would upload the PPTs. And these are the references that I use to present my PPT. Thank you, everyone, and keep smiling just like this characteristic. Okay, bye.